Hello everyone, welcome to a new Stata tutorial. In this case, we're going to be talking about VAR models. I'm going to show you how to produce out-of-sample forecasts and add the confidence bands. My name is Juan Amico, and for those who don't know me, I'm an economist and I create tutorials about time series and applied econometrics. The idea is that by the end of the video, you're able to produce an out-of-sample forecast with confidence bands like this using a VAR model, and also that you can produce a forecast like this. Before we proceed with the tutorial, I would like to let you know that there is a link in the description of the video where you are going to be able to buy the material to replicate the content. This material includes the dataset, it includes the slides with all the step-by-step instructions, and also the do file to replicate the model. It's going to have a code to produce the graphics with all the style that you have seen in that picture before. Also, you will find the following link that contains all my material, all my links, all my social media where you can follow me. You can email me if you need to. And also, you're going to be able to read all the articles that I normally write in Medium, so you can click in here. Going back to our tutorial, we will estimate a VAR model for USA using the variables CPI and money supply. We will analyze the price variation. What we are going to try to capture is how shocks in money supply are going to affect prices. So the steps to estimate the VAR model are going to be, of course, checking the properties of the data. We're going to see if they are stationary. In case that they aren't stationary, we're going to ask, are the variables cointegrated? So to verify that, we will run the Johansen Cointegration test. In our example, we are going to see that the variables are not cointegrated, so we are going to estimate a VAR model and select the proper lag length. Then we're going to do some model diagnostics. We're going to verify if there's autocorrelation, and we're going to talk about the VAR Stability Condition. We will see the impulse response functions and the variance decomposition, and then the most important part for today is going to be how to produce the out-of-sample forecasts and add confidence bands. As I already mentioned, for today's example, we will review how the prices respond to changes in money supply. What we know from economic theory is that in the long run, money is neutral. This means that changes in money supply will only affect nominal variables such as prices, but due to rigidity in prices, changes in money supply may have no effects on prices in the short run. So just to clarify this, we know that money is neutral in the long run. This is, if you print money in a systematic way, there's going to be inflation. But in the short run, yes, prices may take some time to adjust to variations in money supply. So we may not see the translation to prices immediately. It may take some time for money supply to affect prices. So as I mentioned as well, M2 is going to represent money supply. Well, we don't have GDP in here, sorry about that. The transformations, we will apply logs and differences and multiply times 100, so we obtain the growth of the variables, and the frequency of the data is quarterly, goes from 1960 to 2022. We are in Stata. I already have imported the data, and I have also already generated a time variable. If you don't know how to do this, you can watch other tutorials that I have where I teach how to t-set a time variable. So for now, the first thing we're going to do then is check for stationarity. We can just produce the graph, for example, of money supply. And what we're going to see is that it clearly has a positive trend. This already indicates that the variable is non-stationary, as the mean is not constant over time. We can also do the Dickey-Fuller test with D-Fuller, and the name of the variable in this case is M2. And we're going to see that the p-value is very high, it's 1, so we cannot reject the null hypothesis that my series has a unit root. The same is going to be the case for the CPI. I'm going to show you that the CPI as well has a unit root. So now what we need to do then is to apply log differences to make our series stationary. I'm going to do the following. We're going to generate, for example, for money supply, we're going to type just a name, LM2 in this case. So we have now generated the logs. Now we're going to apply differences. Let's call, for example, MS for money supply. And there we go. And we can multiply these times 100. So then we're going to get the values in percentage. We're going to do the same for CPI. We're going to first apply logs. So I'm going to call this L CPI. We apply logs. Next, we generate the differences. Let's call this variable, for example, P for prices. And it's going to be equal to D dot L CPI. And then we multiply times 100 as well. And now, for example, I can show you how the price variation looks like. TS line, and we go with prices. And here we go. This is how prices are changing. Now we're going to check for cointegration. We have verified that our series are integrated of order 1. In other words, our series are non-stationary in levels, but they are stationary once we apply logs and differences. And before we can estimate the VAR model, it is always a good practice to verify that the variables are not cointegrated. We're going to test this with the Johansen Cointegration Test, because if the variables are cointegrated, we don't need to work with a VAR model, we would need to estimate a VEC model. In our example, we're going to see that the variables are not cointegrated, so we would be working with a VAR model. I'm going to show you still how to do this procedure. We're going to run the Johansen Cointegration Test, but before that, we have to tell the software how many lags we want to include in the test. And we're going to check for the amount of lags using the command var soc. Back in Stata, you're going to type var soc, and then you type M2 for the money supply and CPI. If you're wondering why we're using the variables in levels, it's because the cointegration test, we will need to run it using the variables in levels. So we can see that the criterions, Akeke, Han Quinn, Schwartz, they are all suggesting to use 2 lags. So that's how many lags we're going to include in the cointegration test. Now to run the cointegration test, we're going to do is type Beck rank, the name of the variables, which are M2 and CPI, and we are going to tell how many lags. We said we're going to include 2. Here we get the results. So now let's go back to the slides. I'm going to show you how to read the results. Back in the slides, I have here the Johansen Cointegration Test output. We have included 2 lags as it was suggested by the Akaike criterion and all the other criterions as well. The null hypothesis of this test is there is at least 0 cointegrating vectors, there is at least 1 cointegrating vectors, and there is at least 2 cointegrating vectors. If the trace statistic is bigger than the critical value, we're going to reject the null hypothesis. Here is our trace statistic, and here is the critical value. So we would read this the following way. There is at least 0 cointegrating vectors. Is this true? Well, we are rejecting the null hypothesis. We are saying that there are no cointegrating vectors. Then there is at least 1 cointegrating vector. Again, because the trace statistic is bigger than the critical value, we reject the null hypothesis. There is not then 1 cointegrating vector. And then with 2, we don't have any values. And the reason for that is because there can be maximum n minus 1 cointegrating vectors. Remember, we have 2 variables. So if we have two variables, there can only be one cointegrating vector. If we have three variables, there could be two cointegrating vectors, and so on. So in our example, the variables are not cointegrated because we have rejected that there exists at least one cointegrating vector. Now I'm going to show you how to estimate the VAR model. We're going to type the command var, the name of the variables. In this case, we're going to be using them with the transformations, of course. We're going to use first the variable prices, then the variable money supply, and we're going to include 4 lags because then we will verify how many lags we need to include in the VAR, all right? So we have estimated here the VAR model. Now let's go with the command again, var soc. That's going to tell us how many lags we will need to include in the VAR model, right? So it's telling us, for example, the Akaike that we need to use 3 lags in the VAR, and then we have Hanan, Quinn, and Schwartz that are suggesting to use 1 lag. Something very important that you need to know is whatever the amount of lags you use, you have to verify that there is no autocorrelation. So let's suppose that we use 1 lag and then you verify that there is autocorrelation, then you would need to estimate again the model, changing the amount of lags. For our example, we're going to re-estimate this VAR. I'm going to use 3 lags to avoid autocorrelation issues. So I'm going to type lags 1, 2, 3. And now we have re-estimated our VAR model. In this slide, I have now written the formal representation, just in case you're working in a paper, your thesis, whatever it is, and you need to write the model. Well, this is the way you would write the model. All right, so we have the CPI and money supply. We're including 3 lags as suggested by the lag length criteria. So we have that CPI is explained by a constant, 3 lags of the variable CPI, and 3 lags of the variable money supply. Money supply is going to be explained by a constant, 3 lags, as you can see, of inflation, 3 lags of money supply. And if you need to take this to a matrix representation, you would write it the following way. And it's very important also to consider that because we have 3 lags, we would need to do this 3 times. Take a look at this vector. It's having -1. You would need to do the same then, all right? You will need to do the same with -2 and -3. That's why I wrote here these dots, because it doesn't fit in my screen, but you would need to do the constant plus the main matrix. The coefficients of the main matrix come from here. V11 goes here, V12 goes here, V21 goes here, V22 goes here, and like I said, this is the lag number 1, and then you will need to copy, paste with -2, copy, paste with -3. All right, so that's how you would write the model in paper. Now let's take a look at the identification strategy of this model. We're using, of course, the Cholesky decomposition. That's just the default decomposition that is using the software to be able to identify the shocks. And this is also known as the short run restrictions. So the identification strategy is the following. Money supply shocks have no short run effect on prices. As I mentioned, it's going to take some time for prices to respond, all right, because of nominal rigidity in prices, which is the sticky prices concept. Here we have then the main matrix, and we can see that money supply will have no effects in the short run. That's why there's a 0. We're going to see then in the impulse response and the variance decomposition that the first impact of the shock is going to be 0. That's because we have defined this with the Cholesky decomposition. Then prices do have a contemporaneous effect on money supply. When prices change, money supply can change accordingly. That's why we don't have a 0 in here. And if you think about this, money supply, if we know, we can think this as policymakers, we can change money supply by seeing how prices are changing. If you see that there's a shock in prices, well, then you could, you could decrease the money supply to try to, to try to tighten the monetary policy. We're going to see in the impulse responses that that is what's going to happen when there is a shock in prices. Money supply is going to decrease. Here I included a note, it's very important. As we have already talked about this, in the short run, prices may take time to respond to changes in money supply, but in the long run, of course, money is neutral. Money will only create inflation in the long run. And you're wondering, Juan, how long does it take for prices to respond? Well, it will depend on how often central banks increase money supply. Let's suppose that you have a country that doesn't have use of monetary policy, then it may take many quarters, all right? It may take many lags for um, for money supply to have an effect on prices. However, if we are talking about a country that abuses of monetary policy, the transition to prices is going to be very fast. We can think about countries Venezuela right now or Argentina that the price, the CPI, the inflation in Argentina, sorry, is around 100% yearly. So those countries, of course, they are going to have a quick transition to prices whenever they increase money supply. So far, we have estimated the model. We have seen how to write the model. We have seen the formal representation, and we have seen the identification strategy with the Cholesky decomposition. Now we will need to verify the stability conditions and check for the residual diagnostics. So the stability implies stationarity. All you would have to do to check for the stationarity of the VAR is to use the command VAR stable, and you are going to get the following table, and it's telling us that all the values lie inside the unit circle, so the VAR model satisfies the stability condition. If the VAR is not stable, all the tests that we are going to conduct in the model may be invalid, and also the impulse response standard errors are not going to be valid as well. Next, you're going to check for autocorrelation. There should be no autocorrelation in the model. We're going to test this with the Lagrange multiplier test. If your model shows autocorrelation, you will need to try to increase the number of lags in the model. Remember that Schwartz suggested one lag, and if you run the model using one lag, you are going to see that there is autocorrelation maybe, but we have used the Akaike criterion that suggested 3 lags, and with 3 lags, we can see that there is no autocorrelation. So this is the code, the command that you need in Stata, var l mar, and you get the Lagrange multiplier test results. The null hypothesis is that there is no autocorrelation at the lag. So for example, if the probability is bigger than 0.05, we cannot reject the null hypothesis. With one lag, we see that there is no autocorrelation, and at the second order, there is no autocorrelation either because the p-value is bigger than 0.05. So we conclude that in our example, there is no autocorrelation. Something you can try is the Granger causality test as well. The Granger causality test will help us to determine if the variables in the system can help to predict each other. The code or command is var Granger, so type var Granger. You're going to get this output. The null hypothesis of the test is the variable x does not, all right, does not Granger cause y. If the probability is bigger than 0.05, we cannot reject the null hypothesis. So for example, in the first equation, we have that money supply helps to predict future values of p because the p-value is smaller than 0.05. So if it's bigger, the variable doesn't Granger cause. If it's smaller than 0.05, the variable does Granger cause the other variable. All right, so money supply, Granger causes prices. Now we can see in the second equation that prices don't help to predict future values of money supply at the 5%, but they do at the 10%. All right, we have prices. They don't help to predict money supply at the 5% level because 0.08, sorry, is bigger than 0.05, but at the same time, 0.08 is smaller than 0.1, right? So at the 5% significance, it doesn't predict, but at the 10%, we can say that prices do help to explain money supply, right? So it's kind of in the line, this one, and we're going to see that, of course, these results are sensible. So let's move forward now. I'm going to show you how to get the impulse response functions now. We're going to type IRF, set IRF. That's the first command you're going to run. And we are now having a file that says it's active. Next, we need to create, in this case, we need to create a file. In this case, I'm going to call it IRF1. Always make sure to use the option replace, because let's suppose that you try to get again the impulse responses, then when you use the command the option replace, it's going to overwrite the old information. So that's what we want to do for sure. So now we have updated the file IRF1, and to get the impulse responses, we're going to type IRF. We want the graph. Now we need to tell the software what is the file that has the impulse responses. It's IRF1. That's what we have called it, IRF1, right? We need to tell which ones are the impulses. The impulses are going to be prices and money supply, and the responses are also going to be prices and money supply. Here we get the graph. This is what the software is going to produce. So I'm going to go to the slides where I'm going to do the analysis of these impulse responses. Here we have the impulse response functions. I have just modified a little bit the format. I changed the colors and the titles. If you buy the do file, you're going to get the codes to produce the impulse response with this format, with these colors. We don't analyze money supply on money supply shocks and CPI on CPI shocks. We care about the crossed responses. In this case, we have the money supply shock to CPI variation, and we see that this shock is positive, but it's a slight effect, right? It's a positive effect, but it's a slight, and it only lasts around 4 quarters. We see that the peak is around the first quarter, and then it's going to vanish around after the four quarter. And then we can see, for example, a shock in CPI on money supply. So this is what I mentioned before. When there is a shock in prices, money supply shows that it's going down, that it's decreasing. In this case, if the central bank, for example, sees that the prices are increasing too much, then what they would want to do is to start decreasing money supply, start tightening a little bit the policies. So that's what you're going to see, this response, right? It's going to decrease. Now, you can see that the effects are going to take around 6 quarters to vanish. So tightening the monetary policy is actually going to take around 6 quarters, all right, to try to mitigate the effects of shocks in prices. Another result that you may be interested in producing is the variance decomposition. The variance decomposition is going to display the percentage of the error made forecasting a variable over time due to a specific shock. In other words, we want to know how much of the variation in the dependent variable is explained by its own shock versus the shock of the other variables in the system. To get the variance decomposition, we're going to type IRF. Now, we don't want a graph, we want a table. We don't want impulse responses, we want forecast error variance decomposition. That's the command here. We're going to type comma. We need to tell the software where we have stored the information, and we have it in the file IRF1. The impulse is going to be prices and money supply again. The responses are going to be prices and money supply again. And we're going to use the option NOCI. We're telling the software to not include the confidence intervals for the variance decomposition because otherwise the table is going to be gigantic and we don't really care about that. So here we are getting the variance decomposition. Actually, let me modify this. I'm going to copy this command. Let's paste it here. We're not going to include the money supply responses. We don't really care about this. I'm going to care a little bit more about prices. That's what we want to analyze for now. So we're going to go back to the slides and I'm going to explain you the results. Here we have the variance decomposition results, and the way to read this is the following. We can see that because of the Cholesky decomposition in the first lag, money supply has no effects. All right, it's zero. In the money supply has no effects in the short run, but then it does start having effects. We can see that the variance decomposition indicates that money supply can explain up to 8.5% of the variation in prices after 8 quarters. So after 8 quarters, money supply will have explained up to 8.5% of the changes in variation in prices. Now the best part is producing the out of sample forecasts. We're going to use the command fcast compute. We need to define a prefix for the variables that is going to create the software. The prefix I would like is f because then I know that's the forecast. And then we need to tell how many steps ahead you want to forecast. So let's go with 10. So now Stata is going to produce 10 predictions in the future. So let's hit enter. And here you see that we are getting the variables. Just to explain you a little bit, FP is going to be the forecast of prices, and FMS is going to be the forecast of money supply. As you can see, because we use the prefix F, all these new variables have the prefix F, right? So I hope now you understand why we included the F in there. And this LV stands for the lower bound of the confidence interval, and this stands for the higher band, the upper band of the confidence interval. So I want to show you, for example, if we type tsline PFP, we are getting, let me maximize, we're getting in blue the prices. This is the series that we had, and this is the forecast that we have produced with our VAR model. So we can see then the prices will continue to decrease until 2025 Q1. They're going to be decreasing. That's great news. But now we want to include the confidence bands in this graph. So we're going to do the following. To include the bands, the first thing I'm going to do is type browse. It's going to open now our data. We can see here all the variables that we have created. Let's go down. And of course, what you can see is that we don't, all these variables, for example, prices, we don't have the values for Q4, 2023, because these, of course, is future. These are the values that we have forecast. That's great. So here you have all the values that we have predicted for the future with our VAR model. And we're going to copy here. Let's go into the editor mode. Let's see, where is it? Here, editor mode. We're going to copy the first value. This value we're going to copy. And we're going to go to the forecast of the lower bound and upper bound. And we're going to modify the first observation. All right, we're going to paste this value in the first observation. So the graph is going to all start from this point, and then it's going to start expanding to the rest of the values in the bands. All right, so I'm going to show you now what that's going to look like. So we can just close this. Here you get the codes. You can add it to your do file. How to replace the values in the editor. So now let's do tsline. We're going to get the price, the forecast of the price. Let's add the lower bound and let's add the upper bound. And voila. Here we see then this is the graph that we get with the confidence bands. And what I was telling you is that if we didn't include that first observation in the editor, you know how we have copy pasted at 1.89, we wouldn't have had this line. The forecast would have started from here, the bands, and you wouldn't have had, it wouldn't have been starting all from the same point, the bands. So that's why we have done that. It's a way to get some to get some consistent results. So now we're going to close this, and back in the slides, this is how the graph would look like if you add some format to it. You can buy the do file. You're going to be able to edit the graph and get a nice picture like this one. If you're working on a paper, you would like to have your forecast looking like this, then feel free to get the do file, and once you run the command of the graph, you're going to be getting this graph. Now, in the case that you want to see just the forecast and not the actual series, you can type fcast graph, and of course, we're going to use the variable the forecast, right? FP. We hit enter, and here we get only the forecast portion. All right, so this is the forecast portion for prices, and we can see that it's going to go until 2025 Q1. Back in the slides as well, in the do file, you have the command, the codes to be able to produce the graph with this format, adding these nice colors. So if that's something that you would like, of course, it's just an additional, it's all included in the do file. And that's going to be all for today's tutorial. We have covered again how to estimate a VAR model. We have used a different model, in this case a model for prices and money supply, and I have shown you how to produce forecasts with your VAR model and be able to add the confidence bands, so then you can create amazing graphs and be able to either publish or include them in your papers or write articles or even for your business. That's the way that you would create forecasts with VAR models in Stata and add the confidence bands. Once again, thank you very much for watching, and if this is some material that you're interested in, you can subscribe to my channel to get a notification every time that I submit new tutorials about applied time series and forecasting.